In this video, we're going to cover a few more of select stoichiometry problems that really encompass every concept, every important concept that we learned in Gen Chem so far. So let's start. A solution is prepared by placing 20.9 grams of KCl in a 0.8 liter volumetric flask and adding water to dissolve the solid. Then the flask is filled to the mark. So basically it's saying we have this many grams in 0.8 liters of solution. The volume, what is the molarity of the silver nitrate solution if 44.1 milliliters of KCl solution reacts exactly with 34 milliliters of the silver nitrate? So there's a lot of things we can do. First, if you're seeing these grams and you're seeing the volume and you can think, let's calculate the moles and the molarity, that's a good idea. Also, what we can do is, since we're having a reaction, we can write the balanced equation. And we know the balanced equation is going to be KCl plus AgNO3. And then what we would do here is flip the cations to get KNO3 plus AgCl. All right, and silver chloride, that would be your precipitate because silver chloride is not soluble. So, all right, precipitate. Okay, so next step is we want to get into the math of it. So we have our 20.9 grams of KCl, so we can figure out the moles. 20.9 grams of KCl, and the molar mass of KCl is 74.55. So 74.55 grams per mole. And then we can divide those two numbers, 20.9 divided by 74.55 to get 0.28 moles. Okay, so that's good. And we can figure out the molarity too, but we don't really need that right now. So we add more to Martin. Okay, so what is the molarity of the AgNO3 solution if 44.1 milliliters of KCl reacts exactly with 34 milliliters of the AgNO3? So the AgNO3, here's basically what we're trying to do. The AgNO3 has a certain molarity, which we're trying to figure out, put a question mark, which equals the moles that react, which we're trying to figure out, over the liters, which we know, which is 0.034. So we're going to use our stoichiometry concepts from knowing our KCl to figure out the amount of moles of AgNO3. So if we have 44.1 of the KCl solution reacts, now for that we need to figure out the molarity. So we know from before that our KCl is 0.28 moles. We can divide that by the liters of 0.8 and figure out the molarity. And that molarity is 0.350 molar KCl. Okay, so if we have a 0.35 molar KCl, and we know from our equation or question that 44.1 milliliters of it reacts completely with the AgNO3, we can figure out how many moles of KCl reacts with the AgNO3. Figuring out that number of moles, we would use the molar ratio, which luckily in the equation is a 1-to-1, to figure out how much of the AgNO3 was reacted. And then going back to the molarity equation on the right over here, we'd figure out the molarity of that solution. So let's do that. So we would put in our 0.0441 liters of KCl, and then it's X moles. We'd have X moles over that. So we'd multiply the 0.350 times 0.0441, and we end up with 0.015 moles. All right, so now this is how much KCl was reacted. So if we know they're all a 1-to-1 ratio, this amount corresponds to the same amount of AgNO3. So we know that the 34 milliliters of AgNO3 had to have 0.015 moles. If that's the case, what's the molarity? That's what this question's asking for. So let's take a look. We can use this equation that we already have written to write in the moles. So you'd have 0.015 over 0.034 equals a number. Now, let's look at it conceptually before we figure out the final answer. If your KCl, you had a 0.35 molar of it, and it took 44 milliliters to completely react with 34 milliliters of an AgNO3, which all of them are 1-to-1 ratios. Think to yourself and answer this in your head. Do you think the molarity is going to be higher or lower than the KCl? So you can pause the video and think about it. But the answer is going to be, it's going to be higher, because the KCl needed more volume to react completely with a lesser volume of the AgNO3, and they're both 1-to-1 ratios. So we can say, before we even solve this, it's going to be a little bit greater than 0.35. And let's do the math, figure out our answer, and it is. The answer would be 0.454 molarity. So it's always good to think about these questions conceptually to see if your answer makes sense. If your answer doesn't make sense based on what you think, you may have done something wrong. Okay, let's move on to the next one. So if you have a 58 milliliters of 3.6 molar sodium hydroxide, and if right there, you can just calculate the molarity or calculate the moles, honestly. So you can set up the equation while you're thinking about it. Liters equals X moles. All right, we have that. Is combined with 49 milliliters of 1.9 molar magnesium chloride. Same thing, you can figure out the moles. So that's a common thing, and you're going to get that. It's going to be repetitive, where you get a molarity or molarity and a volume, or basically 2 out of 3 of these variables, liters, moles, and molarity. And a good practice would be to calculate the missing one immediately. And then once we have this, we know. So the question is asking for what mass of the solid is formed. Now, if you're wondering, okay, what's the solid? You need to write a balanced equation. Some of these questions may not be as obvious as writing an equation, but if you have things that are combined, reacted, combusted, then those all revolve around a chemical equation. So let's write the chemical equation. NaOH plus MgCl2, right? Magnesium chloride is MgCl2 because it's Cl is -1 and Mg is +2. When you react these, you'd have NaCl plus MgOH2 because hydroxide is a -1 charge. So let's balance it before we get into precipitation. So we have Na, OH, there's 2 OHs here. We make that a 2, and then we make this a 2. That was really quick, but you can see my balancing equations video to more of the rationale behind that. So now this is balanced. And we can take a look at the amount of moles. So let's calculate that for the NaOH, and this is for the magnesium chloride. Okay, so we can do 3.6 times 0.058, and this is going to be 0.2088 moles. I'll write it on the bottom. This is going to be your moles. And then for the magnesium chloride, you have 1.9 times 0.049, and this is going to be 0.0931. So our job here is, when things react, is to always make sure we know the limiting reactant. We want to know the extent of how the reaction occurs, so we can compare both of our reactants to one of the products. And let's compare it to the 2 NaCl. So we have 2 NaOH makes 2 NaCl. So that's a 1-to-1 ratio. We know that the 0.208 is going to correspond to 0.208 of product. So now we look at the MgCl2. We know that 1 mole makes 2 moles. So if that's the case, we multiply this by 2 to get the product molarity. So or product moles. So you take that, multiply it by 2, and you get 0.1862. So look, judging by this, whichever reactant creates the least amount of moles of a specific product is the limiting reactant. Therefore, MgCl is the limiting reactant. So that's a good thing to know. And we can figure out how much or how many moles of either product is produced from that limiting reactant. But the question is, how many grams of the solid is formed? So the solid, by our solubility rules, would be MgOH2. Now, NaCl is soluble because everything that has an Na, that cation, along with most of the group 1A cations, are soluble. But magnesium hydroxide is very weakly soluble, if at all. So this is going to be most likely our solid. So we can write solid there. We want to see how much MgOH2 is produced by the limiting reactant, not by the NaOH. NaOH is not our limiting reactant. So this MgCl2, since it runs out first, we would say, all right, the relationship between MgCl2 and MgOH2 is a 1-to-1 in our balanced equation. So if we have 0.0931 moles of MgCl2, this would correspond to the same exact amount, 0.0931 moles of MgOH2. Now from that, we can multiply by the molar mass of MgOH2, 58.32 grams per mole. And as from magnesium is 24.3. You have 2 oxygens, that's 32, plus 2 hydrogens, that's 2, the 8.3, and multiply it by 0.0931 to get 5.43 grams of MgOH2 solid that is produced. Okay, good. All right, and again, any questions you can write in the comments or check out my other videos. In this last problem, we're going to do very similar to the first problem, where we use a balanced equation to figure out the molarity of one of the reactants that's reacted completely with the second reactant. So let's start. We have sodium thiosulfate, Na2S2O3. It's used as photographic film, whatever. The amount of it can be determined by a titration with iodine according to this equation. So that's good. They give us the balanced equation. Calculate the concentration of Na2S2O3 solution if you have this solution of iodine, which you can figure out the moles from that, 42.9 milliliters of a 0.245 molar I2, and if it reacts with 100 milliliters exactly of the sodium thiosulfate. So the first thing we want to do is calculate the moles of I2, because we want to know how much quantitatively of the amount that reacts. And then we can go backwards and figure out how much Na2S2O3 reacts and figure out the molarity for it. So one step at a time, you have 0.2450 molarity of I2 equals X amount of moles divided by 0.0429 liters of it. So then you multiply those two together to figure out the missing moles. And your answer is 0.0105 moles of I2. Good. So now if we have that, and we can look at our balanced equation, that we have 1 mole of that I2 reacts with, or can react completely with 2 moles of the Na2S2O3. So if that many moles reacts completely with whatever the sample is in 100 milliliters, we know that 100 milliliters has to contain double the amount of iodine, or double the iodine has. So we multiply this by 2 and 0.02. And the reason why we know it's double is, again, because of the coefficients and the molar ratios in the formula. So this is how many moles of Na2S2O3. Okay, so that's the case. Then we can go backwards and see that this solution is 100 milliliters. Now the question is asking for what's the molarity of it. So we have the moles. We can divide that by the liters, which is 0.01 liters. And this would equal 0.2102, or just 0.210 from sig figs. Well, actually, both these numbers have 4 sig figs, so it would be 0.2102 molar. So that would be your answer for the molarity of Na2S2O3 in this question. So like and subscribe to this video and this channel.